Dear learners, welcome to week 5, lecture 3, development of Navier solution for finite shell. First, that review of last lectures. In week 5, in lecture 1, I have presented the state of art for infinite shell, means the concept of generalized plane strain. In lecture 2, I have described that how to develop a code in MATLAB and discuss a recent literature article, I think 2021. In this lecture 3, I will develop the state of art for a finite shell, which is similar, the steps are similar that I have presented in lecture 1, but it is slightly more detailed. Let us consider a finite shell made of composite materials which is orthotropic in nature, and let us say there are layers 1, 2, 3 and up to L, and they are perfectly bonded. Sometimes I may forget to discuss that all the solutions or whatever I have discussed is even the formulation is valid for when layers are perfectly bonded. And material is orthotropic, and solutions I am presenting for a cross ply, basically cross ply composites and sandwich plates, it is valid for that. So, for this case the same displacement field is considered, that u1 is equal to u1 0 plus zeta times psi 1, u2 is equal to u2 0 plus zeta times psi 2, u3 is equal to w naught, and our coordinate system are x, theta and z, where x is your longitudinal, theta is your circumferences and z is your thickness direction. It is a singly curved surface, so radius in one direction, another direction radius is infinity. So, we can say that R1 is infinity, R2 is R, and the lemma parameter A1 is 1 and A2 is R. If we follow these things, we can find out the strains component. There are two ways for a circular cylindrical shell. One way is that you can find out the strain components, which is generally given in cylindrical coordinate system. Most of the theory of elasticity book, that strain displacement relations are given generally. So, one can use directly, but I have already developed a strain displacement relations in very general form. So, that can be find it out through a special case. So, circular cylinder is a special case. So, putting the value of lemma parameters and radius, we can find out the strains. So, from here epsilon 1 R1 is infinity, A1 is 1. So, this term is going to be 0, this term is going to be 0, only contribution will be from this term, and that is epsilon x axis u1 comma x. Then we are talking about epsilon 2 which is basically epsilon theta theta. Here A2 by alpha term will not exist, but these two terms will contribute, and A2 is small a2 1 plus zeta by r, then u2 comma theta plus u3 a2 by r, where a2 is r gets cancelled out, and same where here it becomes 1 by r plus zeta u2 comma theta plus u3. Then epsilon zz is u3 by zeta, u3 is not a function of zeta, so it is going to be 0. Now we can find out the expression of gamma 23. So gamma 23 expression can be say that u2 comma zeta, and this will exist and this will also exist, all three term will exist. Gamma 13 u1 comma zeta, r1 is infinity, so it is going to be 0, and 1 by a1 u3 by alpha, so u3 comma x. And gamma 12 is u1 by a1, so it is u1 comma theta and u2 by a2, so basically r plus zeta, which is not a function of x, and same here r plus zeta will cancel out, it becomes u2 comma x. So finally the non-zero strain components for the present case is written here. First epsilon xx, epsilon theta theta, epsilon zz, gamma theta z, gamma xz, gamma x theta. So if you remember that for the case of infinite shell, our epsilon xx was 0, then gamma theta z was there, but gamma xz, gamma x theta was 0. So there are only 3 non-zero strains basically, this one and this one, all 3 were 0. But for the case of a finite cylindrical shell, only one is 0, epsilon zz, other 5 strains are existing. So this is the expression of strain displacement. If you want to do it or arrange it in the form of, let us say, epsilon xx is equal to epsilon xx naught plus zeta times of epsilon xx1, that can be also done, but in the present case because it is very simple, so I have not did like that way. So one who is formulating only for a cylindrical shell, so one can try in this way, so programming will be easy. Then can we convert our governing equations to the present case? So if we talk about the first governing equation, so 2 comma alpha and 1 comma beta, so derivative of Lemma parameters is going to be 0, and these two terms will contribute in the first case. So we have written the non-zero value of this, and the dynamic is also taken because later on our 6th week I am going to explain the free vibration of cylindrical shells or different shells. So I have taken that, yes, these are some terms will come up, but for the present case we are studying only the static part, we are going to put it 0. In the second equation, first and third term will be 0, second and fourth will contribute, and q2 by r2 will also contribute. So in this way the third equation, first and fourth terms will be 0 and second and third will contribute, and fourth equation, first and third term is going to be 0, second and fourth will be contributing. In the fifth equation, first term is going to be 0, second will exist, and third and fourth, and so on. So if we represent in the terms of x, theta and z properly and writing in a combined form, so this is our 5 set of partial differential equation for a finite cylindrical shell. So in the first equation qx loading, second equation q theta, and third, fourth and fifth. Generally in most of the cases or the review articles or the Journal articles, order is slightly changed. So, 1 second, and this is treated as a third equation W and fourth and fifth. Now, the associated boundary condition edges. Now, this is a finite cylindrical shell. So, now we have a for a boundary two faces are there, that one x is equal to 0 and x is equal to a. So, basically if we talk about this is x is equal to 0 and x is equal to a. So, over this, and one is psi is equal to theta, we can say theta is equal to 0 and theta is equal to psi, this edge. So, I am going to put hash here. So, the normal to this, the normal direction is basically x. So, in the case of boundary condition, we can say that in plane stress resultant nxx or displacement, then nx theta or u2 0, qx or w moment and psi 1, mx2 twisting moment and psi 2. As is over here where theta is equal to psi. So, the normal direction is basically theta. So, we can say that n theta x will be u1 0, n theta theta or u2 0, q theta or w naught, mx theta or psi 1, m theta or psi 2. So, these are the variable which need to be specified. So, depending upon the boundary conditions we can specify. For example, if you say that these edges are clamped, so for that case our all displacements is going to be 0, like u1 0, u2 0, w2 psi 1 and psi 2 is going to be 0 at theta is equal to 0 and psi. If I say that this is my clamped and it may be free, so for the case of free all stresses need to be 0. So, depending upon the boundary condition we can specify our variables. I discuss number of times, and again I am going to discuss is that analytical solution, or I would like to say that closed form solutions are valid for simply supported boundary conditions. If I say that all edges are simply supported, if you let us say 1, 2, 3 and 4, if all edges are simply supported, then the cylinder is said to be Navier support boundary conditions. If any two opposite edges like this are simply supported, then we say that cylinder is subjected to Levy support conditions. Analytical and closed form solution is valid only for Navier support condition and Levy support conditions. If you are interested to solve a problem in which one edge is clamped and another edge simply supported, this edge is free and this is having some point support, then we cannot get the analytical solution or closed form solution. I would like to say that even the approximate solution, approximate means the solution obtained through ridge technique or Galerkin technique, where you can say that all edges are clamped or two edges are clamped, two edges are free. So, in that case we have to also boundary conditions are placed in such a way so that we can get some solution. So, other than the all round simply supported and two opposite edges simply supported, we can get a solution through approximate techniques, and those techniques generally ridge technique and Galerkin technique, and we have also worked on the Kantarovich, so extended Kantarovich technique. So, recently you will find a lot of articles that in which a cylindrical shell or a complete shell is studied using the extended counter-which method. If you see that the loading and boundary conditions are very vague, that in that case the numerical solutions comes into the picture, that you call about finite element solution. And recently that method is DQM, differential quadrature method, or the another technique is state space finite element technique, means combining of analytical as well as numerical technique. So, if we do so, we can get the solution for variety of loading and boundary conditions. Now, let us see define the stress resultant. So, Nxx is sigma xx into 1 plus zeta by R2, R2 is R. So, it will be there. If you talk about n theta theta, n theta theta will be minus h by 2 to plus h by 2, sigma theta theta into 1 plus zeta by R1, R1 is infinity. So, it will not have those terms. Similarly, here you can see that nx theta and n theta x, if you talk about nx theta, so curvature in the second direction will participate, and n theta x curvature in this direction will participate. So, here we can see that for a cylindrical shell, nx theta is not equal to n theta x. Similarly, defining the moment resultant, then mxx, m theta theta, mx theta, m theta x. So, here just putting the zeta over here, multiplying with the zeta, sigma xx 1 plus zeta by r into d zeta is the definition of mxx. Then the definition of m theta theta will be zeta times sigma theta theta into d zeta, and mx theta and m theta x. So, here again mx theta not equal to m theta x. Now, can we define the shear, that qx and q theta? Qx will be tau xz 1 plus zeta by r, and q theta will be just simply tau theta z and integrating over minus h by 2 to plus h by 2 d zeta. And the loading at the top and bottom equal to the traction, that whatever, for example, I would like to say that, let us say in the case of a plate, if you apply a qz, so that will be equal to sigma zz. So, loading per unit area, because it works on that complete area. So, if you do so, then it will 1 plus zeta by r factor comes over there, and tau zx, tau x theta and sigma zz. So, ultimately the applied traction equal to the resisting traction or inside stresses, that at the boundary basically. Now, we have to define the shell constitutive relations. So, somebody has done for a plate constitutive relations. Now, I am saying that it is a cell constitutive relations. So, using the basic constitutive relations, that sigma xx is equal to q11 into epsilon xx plus q12 into epsilon theta theta, sigma theta theta equal to q12 epsilon xx plus q2 epsilon theta theta, tau x theta is q66 gamma x theta, tau zx q55 gamma zx, tau theta z q44 gamma theta z, where q11, q12, q22, q44, q55, q66 can be represented in terms of engineering constants, basically orthotropic, that E1, E2 and mu12, mu21, G23, G12, G31. So, for a composite material, so you can find out all Q, Q1, Q2, Q3. So, already I have discussed in the second lecture of week 5 that how to evaluate through a coding, that you first give through a program E1, E2 and E3, mu12, and then you have to evaluate Q1, Q2, Q3, and then later on I have also given the formula for a transformation of a Q1 bar Q2 bars. Since I said that present formulation is valid for a cross ply cylindrical shell, definitely one can develop a solution for a angle ply cylindrical shell, but here more generalized. So, Q16 and Q26 will also come into the picture, and we have to present like symmetric and antisymmetric case the analytical solution are valid. But for a general, if you are interested to angle ply finite shell, then the solution is analytical solution is not valid. Then we have to think for a approximate or finite element solution. Let us see nxx. Nxx is epsilon x sigma xx into 1 plus zeta by r into d zeta. So, sigma xx is replaced by this. So, now explicitly writing, substituting the value of epsilon xx and epsilon theta theta. This is the value of epsilon xx. This is the value of epsilon theta theta and 1 plus zeta by r. So, if you keep inside that, so here 1 plus zeta by r come into the picture Q11, but in the case of Q12 only 1 by r will come up and 1 plus r by r plus zeta will get cancelled out and it becomes like this. Here one can see that we can write the coefficients basically. It will be Q11 minus zeta by r2 minus h by 2 plus h by 2 into d zeta, and then next will be zeta times of Q11 integration over there. So, first term will give you the definition of A11, second term will give you the definition of B11, and similarly here if it is zeta times the definition of B11, zeta square the definition of D11, and here again it is the constant. So, the definition of A12, and if you multiply with this B12, and again this is the coefficient of W naught will be also B12. So, if we do so, ultimately nxx can be represented A11 plus B11 by r u10 comma x plus A12 u20 comma theta plus W naught divided by r B11 plus D11 by r psi 1 comma x plus B12 psi 2 comma theta by r. This I have explained in the lecture 1 also of week 5. So, only thing is that now we have slightly bigger form. The basic idea remains same, but now it is slightly bigger form because we have more terms. In the previous case we do not have epsilon xx, we have only epsilon theta theta. So, now the terms corresponding to epsilon xx now slightly increased. When we are going to solve for a n theta theta, so n theta theta is basically minus h by 2 to plus h by 2 sigma theta theta into dz. So, sigma theta theta is basically Q12 into epsilon theta theta plus epsilon xx plus Q22 into epsilon theta theta. So, epsilon xx is fine, but when you talk about epsilon theta theta, it contains a term 1 plus zeta by r upon 1 by r. So, if you take upside over there, so 1 plus zeta by r raised to power minus 1. In the previous lecture also that 1 plus zeta by r inverse can be open up in infinite series, but we are going to consider up to quadratic terms. So, most of the literature that Flaget's theory they have considered the term up to quadratic, and basically this gives a more accurate solution if we take the more terms that at least up to quadratic. If we take even or cubic and then there is a less contribution for that. So, 1 plus zeta square by r square term is considered. Then even during the integration if something becomes zeta cube by, because zeta is outside sometimes, so r square, so then we are not going to integrating, we are leaving it. So, by following those approach, and theta theta is written like this A12 U10 comma x A22 minus B22 by r plus D22 by r square U20 comma theta plus W naught upon may r and B12 psi 1 comma x, and this is the coefficient. I have explained for 2 nxx and theta theta. So, by following the similar procedure, one can get the expression for nx theta and theta x. So, when we get the expression like this, then this expression is known as cell constitutive relations. Similarly, one can get the relations for mxx. Mxx is minus h by 2 2 plus h by 2 sigma xx 1 plus zeta by r into zeta and d zeta. So, if you substitute all these things, some relations, and similarly m theta theta, mx theta and m theta x. So, I am not going to write specifically all the terms. One can derive, it is very easy, just one has to substitute the terms and finally writing the coefficients. So, ultimately all the coefficients like A11, A22, A21, A12, Aij, and the coefficients are Bij and coefficients are Dij are written that minus h by 2 2 plus h by 2 Qij, which it is multiplied with 1, they will be known as Aij. When it is multiplied with the zeta, it is known as Pij. When it is multiplied with the zeta square, it is Dij. Here the term small Kij square is used. This is saying that is Kij is 1 except for K44, or basically when we say that A66 shear correction factors A44 and A55. So, there it is going to be K square 55 is also there. Shear correction factor, it is going to be 1 otherwise it is taken 0.91287. So, for a single layer one can integrate and find out the value ultimately, but for a composite panel, as I have discussed in programming also, we have to take the coordinate system, that each layer thickness and the cube difference of the cube and divided by 1 by 3. So, ultimately these are discrete layers, we are adding summation of all the layers material property. So, kth means the kth layer. So, it goes from 1 to L. So, we can add all this. So, though it is a equivalent single layer theory, means we are solving a single layer, but using the concept of summation we can get a solution for a composite layer. If somebody is interested to have a very accurate solution, like the at each layer interface, what is my shear stress variation and all these things, for those cases layer wise theories are used, in which each layer has number of variables. In the present case, the variation of u is assumed linear across the thickness and w is constant along the thickness. So, w0 and ui I can say that u1 and u2. But if you talk about a layer wise theory, so in that in each layer it is linear, so it may have some kinkiness, so it can represent the local behavior. So, the theory I have discussed here, that is valid for a thick shell theory, but it may not give very accurate result for if you are interested in the interlaminar shear stresses. So, for that case either one should try for a 3-dimensional solution or the layer wise theories. But in general, if you are interested in the deflection behavior or in plane bending stresses, they are pretty good, but the shear stresses means transverse shear stresses, they are away from the 3-dimensional solutions, slightly away from the 3-dimensional solutions. So, ultimately first equation, second, third, fourth, fifth. So, if we substitute all the value of mx theta, nx theta, qx, q theta, if we substitute all in the main 5 partial differential equation, that leads to a this set of equation, that L u is equal to p, where L is a differential operator, that L it contains, it is a 5 by 5 matrix, that L11, L12, L13, L14. The importance part is that here Lij equal to Lji, L12 is equal to L21, L13 is equal to L31. So, we need to only get the non-zero value of upper half, and then we can say that lower half is same value. So, now I have written that, let us say L11 is equal to F1 and some terms, let us say it is coming comma xx plus F2 whatever terms comma theta theta. So, F1 and F2. In the previous lecture L1, I have clearly said that F1 may be A22 plus B22 by R plus D22 by R square and so on. So, F1, F2 are nothing but the coefficients of any terms which is having comma xx. If you are talking about particularly L11, so basically U10 comma xx plus U10 comma theta theta, that is L11. L12 is U20 comma x theta. And so, because it is multiplied with this, so in that way you can find it out. So, W comma xx and W comma theta theta. Only thing is that our fifth equation is placed here at third position. So, we have obtained this psi 1 and psi 2, and these are our loading P1, P2 and P3. I have not presented the all individual component what is F1, F2, because I have already given the details in lecture 1. So, one can derive or one can find out the actual component of F1 and F2. So, in this lecture I am just presenting the overall picture, that how do you proceed for a solution of a finite cylindrical shell. For a solution that simply supported shell, that the boundary is x is equal to 0 and a, the following variables need to be specified, that W naught transverse deflection is going to be 0 and the longitudinal deflection u to 0 if you talk about a shell like this. So, this is your u2 basically u1 u2 W, and then over this edge it will be u2, this will be this will be u10, u20 and W naught. So, if you are talking about x is equal to 0, so this is the edge where we are going to specify the boundary condition, and this is the x is equal to a. So, W going to be 0, u10 cannot be, so instead of that nxx is specified. So, nxx is 0. Then moment mxx is 0. So, basically psi 1 and psi 2 rotations. So, here instead of n x theta u2 0 is longitudinal. So, if we do so, that u2 is 0, psi 2 is 0 and W naught, then only we can assume the solution in a Fourier series, otherwise we cannot get the solution. So, this is the hard simply supported condition, and then theta is equal to 0 and theta is equal to psi, there you have to simply support it. So, W u10 psi 1 and n theta theta and m theta theta. So, if you see that at x is equal to 0 and a, at theta is equal to 0 and psi, W is 0. So, definitely straightforward we can assume W in x and theta direction is sine series. If you put x is 0, sine is 0. If you put x is equal to a, then sine is 0. If you put theta is 0, then sine is 0. If you put theta is psi, then again it is going to be 0. So, in this way the expression satisfy the boundary condition exactly. That is why sometime it is called is the exact solutions, and then the variable u2 0. So, u2 0 is 0 where x is equal to 0 and a. So, along x axis it is 0. So, along x axis u2 is assumed as a sine series, but along theta direction it can be assumed cos theta. And the same way u1 0 is 0 along theta direction. So, u1 0 is assumed sine series along theta direction and cosine along x direction, and psi 1 and psi 2 follow the similar procedure. Here the first sin mx and sin n theta. So, when a cylinder is subjected to skew symmetric loading, then the solution is expressed like this, and ms is 1 here. If the cylinder is having symmetric loading, means that around the theta the loading is symmetric, then the solution will be assumed sine and cos. So, this is the most important part. So, generally most of the cases skew symmetric case, the problem is solved in the literature. For the symmetric case it becomes further special, basically it independent of theta, and then axisymmetry case can be done. So, the problem is more simpler. So, the more general problem is the skew symmetric loading, where loading is expressed like this. Now, we are interested that how do we represent nx, n theta theta, mx, m theta theta, or nx theta, n theta x. They will be sine, cosine function or cos function. So, for getting this, so first we have to, based on the boundary conditions, we can only express these 5 variables displacement fields. So, after that, if you are sure that displacement field would be such that, then using the constitutive relations one can find that sigma xx is sin sine or sin cos or cos sine. So, epsilon xx, epsilon theta theta and gamma x theta. So, sigma xx contains q11 and q12. So, epsilon xx is this much, u10 comma x plus zeta times I1 comma x. So, u1 is expressed cos and sine. So, if you derivative with respect to s, it becomes sine and sine. Similarly, u theta comma theta or u20 comma theta, that becomes again sine and sine. So, sigma xx and sigma theta theta will be expressed in terms of sine series, sine and sine, both in sine. So, we can see that nxx is what? Just the integration of thickness direction. It is not changing with along in plane direction. So, nxx, n theta theta, mxx, m theta theta can be expressed in terms of a same way sine series as our w naught is expressed. Then we talk about the nx theta. So, for that tau x theta gives you expression of cos and cos. So, nx theta, m theta x, mx theta, m theta x will be represented as cos series. Some of you may ask, why are you worrying about, ultimately we are going to solve only displacement. We will solve the displacement, but at the end of the day we are interested to find out the variation of stress resultants or the stresses ultimately. So, this will give you the actual variation. Definitely there will be some magnitude, basically sigma xx mn or nxx mn, there will be some magnitude, but they will follow this path, mode of type. Then tau z theta and tau zx. So, they will become sin m theta and cos n theta, and tau zx becomes cos m bar x and sin n bar theta, where m bar or n bar. So, basically m bar is equal to m pi by a and n bar is equal to n pi by psi. So, similarly q theta and qx is expressed because it is just integration of tau z theta and tau zx. So, sin cos and cos sin. Now, if you substitute, okay, before going to there, the loading, that qz or q theta is known. So, if you find out the Fourier series. For the case of infinite, it will be 2 by psi, but now it is integration over twice, 0 to n and 0 to psi. So, 4 times psi a and q, which is a function of x and theta, sin n par theta and sin m pi theta, and this is the area. So, most of the time for the two dimensional theory, qz is presented at the reference plane where z is basically zeta is 0. So, ultimately if you substitute all the sign expression into L, that gives you a matrix K and U equal to P. So, from here you can be find it out K inverse of P. So, the solution of a simply supported finite shell can be obtained where only term is R is the mean radius. So, at any location, so zeta times, if you say that at any up and down, so r plus zeta, if you put there the value of zeta, you can obtain the strains, stresses and so on. Now, in the previous case, the post processing, like our stresses, if you talk about that sigma zz comma z or tau zz comma theta or tau zx comma z. So, all are transverse stresses. So, we are interested to find out sigma zz, tau z theta and tau zx. Already we have used in the shear correction factor, that is fine, but still there is some inaccuracy. So, if we do the post processing technique, this is the journal 3-dimensional equation of equilibrium. If we convert to in our system, then it becomes equation like this, and ultimately in that if you talk about in the second equation for a static case going to be 0. So, from here tau z theta can be obtained like this, that sigma theta theta comma theta plus tau x theta comma x multiplying with that integrating over this f plus 1. This is the integrating constant. Then same way tau zx and sigma z star can be obtained. Why we have put star? Because they are different than the we have obtained through constitutive relations. So, they are slightly different. So, we put it star here, we have obtained through the post processing techniques. So, very first paper in this field, that static bending of cylindrical shells or the composite shell, arrived in I think 1964 some time that. So, and there is another paper, that static analysis of moderately thick finite antisymmetric angle ply cylindrical panel and shell. So, that has come in that 1989, 1991 generally. So, in this paper a cylindrical shell is studied, a simply supported boundary condition. It is clearly written that they have used that Flage type shell theory and Galerkin approach, and literature survey is presented. Just I am going to the theory part. Yes. So, one can see that the strains are expressed epsilon 4, epsilon 5, epsilon 6, epsilon 3 is 0, and in terms of displacement field they have represented like this. So, here kappa 1, kappa 2 is basically epsilon 1, 1 of 1, epsilon 2, 2 of 1 and so on. So, it is FSDT type theory, and so these are the governing equations are obtained. Here you can see that for a antisymmetric angle ply, I said that one can develop for a angle ply case, but we have to be very particular, sometimes antisymmetric or symmetric, so that some coefficients can be going to be 0. If we are interested to a general angle ply, then it is very difficult to develop a analytical solution. So, these are the governing equations are expressed. So, if you remember that Ni, Mi, so the coefficients are expressed Aij, Bij. So, these are the standard way of representing the coefficients. So, how do we represent these coefficients A5, 5, A4, 4, and if we substitute all these things into the partial equation and the boundary conditions, that either this un or nn, ut or nt at x is equal to 0 and then so on. So, they have solved this step. So, my aim of this you tell you that yes, the same way we have did it, that u3 the deflection is assumed in sine and sine, then u2 is assumed cos and sine, and u1 is assumed sine and cos. So, in this way the solutions are presented. The students or the learners can go through these papers and can understand, and definitely I would like to discuss some results here. So, you can see that the results are presented for different a by h when m is equal to n, then taking the terms m 10 and 20, then we are getting the converged this whether 4, 6, 8, 6. So, number of terms are required, and this is theta degree and 0 degree, 22 degree, and u1, u3, phi and m are compared. Here one can see that moments are compared, plotted along the x by a, and they are calculated at b by 2. The same way that along the theta the different moments are calculated, bending moments. So, those days in 90s, 80s or 70s, that time computer was just started. So, very preliminary results were presented like the bending moments or the deflection, but after 95 when the use of computer has increased, so we are able to find out the more detailed results and the various parametric solutions. So, even these days you can directly use your CAE packages like can say Sabacus or Nastran or or any structural analysis software, that you can directly get the deflection, stresses, resultant. But the aim is to tell you that the basics behind that, how these different softwares has come up. So, behind that there are the simple theories. Even we can for a research these days, if some people are working on that carbon nanotube, that shell is made of carbon nanotube or shell is made of graphene sheets, and what will be the deflection. So, definitely some different material model is required, but the basic remains same. So, even the functionally graded shell and the buckling of shell, functionally graded shell is currently studied. So, with the basic models definitely we can go for a complex one. So, with this I would like to thank you very much.